This video uses the Riemann tensor to calculate the curvature of flat space using spherical polar coordinates and then the curvature of the two-sphere. It then looks at the addition of a term to the Einstein tensor in the form of a cosmological constant and what it says about the curvature and energy density of the universe. Let's begin with extrinsic curvature. Now, the extrinsic curvature of a surface depends upon how it is embedded within a higher dimensional space. So take the example of a cylinder. The surface of the cylinder appears curved when viewed from three-dimensional space, even though it is really just a flat sheet rolled up until its ends meet. A two-dimensional being restricted to the surface of this cylinder could draw a triangle whose angles sum to 180 and conclude that the surface was flat and not curved. This two-dimensional being could also draw a circle on the surface of the cylinder, and the circumference of this circle is still 2 pi r. Now, intrinsic curvature. So the intrinsic curvature of a surface does not depend upon any embedding in higher dimensional spaces, but depends upon relations between points within the surface. So a two-dimensional being restricted to the surface of a sphere would draw a triangle whose angles sum to more than 180 degrees, and so would have to conclude that the surface or space is curved. Now, the Riemann tensor is the instrument that can tell us if intrinsic curvature occurs in a given space. And so here's that object here. And so we're going to work with this tool in this video. Alright, so let's start with spherical polar coordinates to describe an arbitrary point in three-dimensional Euclidean space, so x, y, z. We'll call the coordinates x1, x2, x3, and r, theta, phi. Now, x is r sine theta cos phi, y is r sine theta sine phi, z is r cos theta. Now, the position vector of an arbitrary point in Euclidean space is given by this object here. And if we put in the spherical polar coordinates, it takes this form here. Basis vectors, unit basis vectors in Euclidean space, ex, ey, ez. Right, with basis vectors and spherical polar coordinates being given by now, so in the spherical polar coordinate system, the basis vectors are now given by these objects here, which is the partial derivative of the position vector with respect to each of the coordinates in turn. So dr gives us this object, dr d theta gives us this object here, and e phi gives us, or dr d phi gives us this basis vector here. So a basis vector in the r direction, theta direction, phi direction. Now the metric for these coordinates is found using the scalar product of the basis vectors. And the metric tells us how to calculate the distance between any 2 points in space. Alright, so the metric is given by this object here, which is each of these scalar products. And when carried out, we find that the off-diagonal terms are 0, as you would expect in flat space. So 1 r squared sine squared theta, and that's an indicator that we are in flat space, that the off-diagonal terms are all 0. Okay, or writing the metric components each, there they are. Alright, to compute the components of the Riemann tensor, we need to calculate the Christoffel symbols of the second kind. That's these objects here, this gamma with the upper index c and the two lower indices a, b. Now the partial derivative of the basis vectors with respect to each of the coordinates, xb here, will give us the Christoffel symbol times a new basis vector. So for example, we take the basis vector in the r direction, partial derivative with respect to r, well, it gives us 0. So that implies that when we expand this out, that is when we sum over c, there's one upper c here, one lower c here, so we sum over them, so there's r, theta, theta, phi, phi, so they're all 0. And that implies that the Christoffel symbol, where both lower indices are r and the upper indice is c, is 0 for all c, meaning that the c can take all values r, theta, phi, and this will be 0. Let's look at the next basis vector, partial derivative of er with respect to theta. When we carry out that partial derivative, we get this object here, and we find that that is equal to 1 over r times the e theta vector. That's the basis vector in the theta direction. So and that then is equal to, as we've got this rule up here to tell us, that this Christoffel symbol times this basis vector means that we have, in this case, if you look here, the C is theta down the bottom here, so that's theta, so that must be theta as well, and we have gamma theta r theta is 1 over r. So this is one way to compute the Christoffel symbols. There is, of course, another way, which we will see later. Alright, so our first Christoffel symbol here, or second actually I should say, gamma theta r theta is 1 over r. Next one, the basis vector in the r direction, er, e subscript r. Now we take the partial derivative of that with respect to phi, and we get this object here, which we find is equal to 1 over e phi. If we look back a couple of pages, we'll see what e phi is, and we'll see that 1 over r times e phi will give us this object here. And that tells us that that's gamma c r phi e c. Well, in this case, c, the lower index here, c, is phi, and so therefore the upper index here must be phi as well. So gamma phi r phi is 1 over r. So there's our next Christoffel symbol. Let's try now the basis vector in the theta direction and take the partial derivative with respect to the coordinate r, and we get this object here, and we find that's equal to 1 over r times e subscript theta. So that's equal to this object again, and so the subscript c there is equal to this theta, and so this c up here must be theta as well. So gamma theta theta r is 1 over r, and repeat the same procedure for the basis vector in the theta direction and take the partial derivative with respect to theta, and we produce this object here, which is equal to this, and so that tells us that this Christoffel symbol is this, minus r. Again, with the basis vector in the theta direction, the partial derivative with respect to phi produces this object, and we get this, okay, which is equal to this, and so that tells us this Christoffel symbol is this one. And continuing, now the basis vector in the phi direction, we do each of these, we get this one is 1 on r, this one cos theta on sine theta, and finally this one with respect to phi gives us this object here. Now watch out here, because it turns out that this one here is equal to minus r sine squared theta er minus sine theta cos theta er. A bit of playing around will give you this result here, and that tells you that the Christoffel symbol, gamma c phi phi e c, has to be summed over two values for c, that's r and theta, r, theta, theta. And so what that tells us then is that gamma r phi phi is minus r sine squared theta, that's this object here, and gamma theta phi phi is this object here, so minus sine theta cos theta. Keep going, and in summary we have all of these, there's all the rest, quite a few of them are 0, all these ones down here. So in 3D the Riemann tensor has 81 components, but with the following symmetry properties this number can be reduced. So the Riemann tensor has these symmetry properties here. If you notice here that the final two indices CD are swapped with the first two, AB, and there's no change in the value here. These two are equal to each other. But when we start swapping, say, A and B to get BA, we get the negative. Riemann tensor, we get the negative value of it. And similarly with the last two indices, C and D, swap those, DC, you'll get the negative value as well. Okay, now, due to these symmetries of the Riemann tensor, the number of independent components is reduced to, if you have a look in here, substitute n as 3 in here, and you'll get 6 independent components. And there's a separate video on all of this, how that comes about, so I won't go into that here. And the individual components are, again, found in that other video, is all these. It's all of these. All right. Now, so let's calculate a few of these to see what happens using the Riemann tensor. Alright, so let's start with all the indices being r. When we evaluate that, this is straightforward. Sum all those out, that all disappears and becomes 0. If we try r theta, let's put those in, if you follow, and you need to make sure you have the Riemann tensor's general form and then substitute in very, very carefully, otherwise you will make errors, so be very careful. Or you could use a program like Mathematica or some other program to sum over the indices and produce your result. Either way, these first two are 0. Let's try this one. Again, summing very carefully, because see the new and the new over there. Once we've substituted in, the only unknown indices are the new here, one up, one down, so we have to sum over those. And new, again, we have to sum over those, so they're going to take the separate in turn values r, theta, phi in turn. And when we do that, we get all this. And when we evaluate, we come out with 0. Theta, phi, same thing again. Notice the new and the new. Now we have to sum over those, one up, one down. And when we do that, write that out carefully, evaluate the terms, we'll come down to 0 again. Still in flat space, if you remember. Alright, and theta, all theta now, same thing again, just evaluate all the way through, and we'll come down to 0. Now all 81 of the Riemann tensor components are 0 in this space. Not surprising, we're in flat space. And all of the contraction of these components will also be 0 because we're in flat Euclidean space. Alright, now let's consider what a 2D being restricted to the surface of a sphere could determine about its curvature. So here we are, spherical polar coordinates, but now the size of the radius of the sphere is going to be fixed, so it'll be a constant. So our coordinates x, y, z become x1, x2 is phi, theta. They're the only two variables. The radius is now fixed. It's now a constant. Spherical polar coordinates gives us this object here where the radius is fixed at a, the value of a. So the only two variables we have are phi and theta. And an arbitrary point on the surface of this sphere is given by this object. Here's a position vector. Here it is again. Alright, now the basis vectors and the new coordinates are, there's only going to be two of them now, e theta, e phi, dr d theta, dr d phi. Here we go. Here's our basis vectors. Alright, the metric tensor GAB is given by this object again, much reduced. Been going from 3 to 2 dimensions, so it just produces this object here. The off diagonals are 0, and we've got a squared sine squared phi. Here we are. Now the Christoffel symbols are found by this object here, the partial derivative with respect to each of the coordinates. It gives us this object. Now d theta d phi will give us this object here, and that's equal to cos phi on sine phi e theta. That gives us is equal to, again, here's our rule, one index, unknown index c up the top and c down below, so we need to sum over those. There's only one vector here, c is equal to theta, and so gamma theta phi theta is this object. d phi d theta gives us this object here, and we take partial derivative of e phi with respect to theta. That gives us this object here in terms of the basis vector e theta, and so gamma c phi theta ec, theta is c, so that's c as well, so gamma theta phi theta is this object. Now, the other method of finding Christoffel symbols is to apply just this formula. That's the general formula for Christoffel symbol of the second kind, and then you just need to substitute in and evaluate. And for instance, gamma theta phi, this object here, and you just go through and evaluate all of them. It's a longer method, and you end up with this here. Carry out that operation, you end up with this. And so gamma theta phi theta is cos phi on sine phi. That's one way of doing it, just the application. The other way is, as you've just seen in the last few slides. Applying that formula again, keep going, and I'll keep quoting the formula again so that you can compare it. So that's I is theta, m is phi, k is phi, put it all in here. There you go, like that. Just evaluate, and you're fine. If you keep going for a while yet, alright, we'll come down. Now, we find the Riemann tensor components. Here's the Riemann tensor again. And let's put in some components. Alpha is theta, mu is phi, gamma is theta, beta is phi. Put that in there, substitute. When you work through, evaluate the components, you'll end up with this, and you'll end up with 1. Alright, we just need a few more of these, so let's have a look. And quoting the formula again. Now, putting in components, this time all thetas. When we do all that, we come down to 0. This one, theta, phi, theta, theta, put that in, again, all come down to zeros. R, phi, theta, put all those in, coming down to 0. Perhaps one thing I haven't mentioned too is when you substitute in your Christoffel symbols, you have to remember some of them, like these first two terms, have to be partially differentiated with respect to whichever coordinate's relevant. So I haven't really emphasised that much. So just be careful there, make sure that's done accurately. Let's keep going. Phi, theta, phi gives us 0. Theta, 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 phi, 0. All phi's give us 0. So in 2D, there is a single independent component of the Riemann tensor, n equals 2. Substituting that, you find there's one independent component. We already found what that is, and that's this one here. So our next job now is we can lower the first index, this theta here, using the metric. So g theta theta, subscript theta in both cases, in the covariant position, times the component. We'll lower that theta there, and when we do that, if we go back to the metric, we'll find g theta theta was a squared sine squared phi, and what we have now is the Riemann tensor with all 4 components lowered. And this is the basic object we're going to work with. And let's go over to the next page. So there we have, there's our basic object here, r theta phi is this object here. Okay, and we work with the Riemann tensor with all 4 components lowered, and that's our Riemann tensor. That's the basic object we work with from now on. Next bit. Now the Ricci tensor is a rank 2 tensor, whereas a Riemann tensor is a rank 4 tensor. So how do we go from a rank 4 tensor to a rank 2 tensor? We need to contract on 2 indices. And a contraction always reduces the rank of a tensor by 2. And so the Ricci tensor with 2 lower indices is the inverse metric, with both indices raised, multiplied by the Riemann tensor with all 4 components lowered. And what we will do is that will contract on alpha and beta there, and we will be left with an object that has just 2 indices. So the one up index sums out with the one lower, beta sums out with this beta, and we're left with mu, mu. Now, so that's how we've gone now, taken this rank 4 object down to a rank 2 tensor. So let's calculate, what will we have? Well, in 2 dimensions here, you've got theta and phi, so let's look at the different combinations. So r theta theta, okay, well let's put that in here. Well, if we do that, that means that the mu and the nu are theta and theta. Now we know from the metric there were 4 terms in that metric. It was a 2 by 2 matrix, 4 terms. So we could have phi phi, that was non-zero, and theta theta, that was non-zero. The other components, g theta phi or g phi theta, was 0, so they don't appear in the sum here because they're just 0. Okay, well let's put that in. G phi phi, if we look back at the metric a few pages back, we'll see that g phi phi, where the phi are both in the contravariate position, was 1 over a squared. This object here, as we saw on the previous page, was a squared sine squared phi. This one here, g theta theta, is 1 over a squared sine squared phi, and this object, as we found, was 0. When we perform that operation, this bit disappears, and we're left, the a squareds cancel out, we're left with sine squared phi. Let's have a look at r phi phi. That's g alpha beta again, r alpha phi beta phi. Alright, now what form could this take? Well, we could have g theta theta, we could have g phi phi, and as we found earlier, g theta phi, g phi theta, all in the upper positions are 0. And so we can take g theta theta times this object plus g phi phi, both in the contravariant positions, times this object. Now this object here is 0. G phi phi, as we saw earlier, is 1 over a squared, but that's times 0, so that will disappear. G theta theta is 1 over a squared sine squared phi. This object here is a squared sine squared phi, so this gives us 1. Now, r theta phi, when we do that, we'll find that that is equal to r phi theta is 0, because if you have a look up here, we're going to be what we would be summing over. Alright, so you can work that through. You'll find they're 0. Next one. The Ricci scalar is a rank 0 tensor, whereas the Ricci tensor is a rank 2 tensor. So again, we need to go down by 2 ranks. And we do that with a contraction. So we're going to contract over the mu, and the mu, and the nu, nu. We're going to 1 up, 1 lower, 1 up, 1 lower. We will sum them out. Okay, so here we go then. G phi phi. Well, if mu and nu are phi, then down here they must be phi as well. If we go here, g theta theta, then they must be theta theta as well. If we had two more terms over here plus g theta phi, then we would have times r theta phi, which we've seen as 0, so they're not relevant to the calculation, they all drop out. It's only these two that are non-zero. G phi phi is 1 over a squared times 1, plus 1 over a squared sine squared phi times sine squared phi, as we saw this one in the previous page. And when we do that, we get 1 over a squared, plus here the sine squared phi's cancel, and we're left with 1 over a squared. Add those together, we get 2 over a squared. So the Ricci scalar for a two-sphere is 2 over a squared. So we see that this is not 0. We see that the Ricci scalar is 2 over a squared. Right. So the Riemann tensor has identified this space as being curved, since not all of its components are 0. And the Ricci scalar, or curvature scale, tells us that this space has constant curvature given by 2 over a squared. So this is a space of constant curvature, whereas flat space would be 0. In flat space, all the Riemann components are 0. But in this curved space, the surface of a sphere, not all the Riemann components were 0. One of them wasn't. And that's how we end up with a curvature scalar, which gives us the curvature of the surface. Right, a sphere is a highly symmetric object. The Riemann tensor for a maximally symmetric space can also be found using, here's the Riemann tensor, but can be found for this for a maximally symmetric space. So for our sphere, substituting in g theta theta, g and so on, we find this is a squared sine squared phi. Next step, put in the ends. 2 minus 1 is 1 times 2, so that gives us 2, r over 2. This object is a squared sine squared phi times a squared. These are all 0, as we saw earlier. That's equal to a squared sine squared phi. When we do that, some a squareds on both sides and sine squared phi's on both sides will cancel, and we're left with r as 2 over a squared. The curvature scalar telling us about the curvature of the surface is not 0. And it's constant. If you look at this, it's constant. So it's a surface of constant curvature. So confirming that the two-sphere is a maximally symmetric space. Cosmological constant. So let's just have a look at the Einstein field equation, this object here. Right? It admits the possibility of the addition of an extra term, now called the cosmological constant, and that takes the form as this, lambda times the metric g alpha mu. That's the addition there. Now this term can be legitimately added because it preserves general covariance. As coordinate variance is symmetric tensor here, it's rank 2 of rank 2 and has 0 divergence. So they're the reasons it can be put in. It maintains the covariant form, or coordinate invariance, and so we can that can be allowed under those conditions. Alright, our coordinate covariance referring to the fact that it has the same form in all coordinate systems, as tensors should. Alright, now the divergence. We take the divergence of the left-hand part, they'll give us 0, and the divergence of the right-hand part, conservation of energy, matter and energy, so the divergence of this is 0, and that's equal to the left-hand side. Divergence of this is 0, and the divergence of this object is also 0 because the covariant derivative of the metric is 0. And so it all agrees. Now, the divergence of the left-hand side is always guaranteed to be 0 because the Einstein tensor is derived from the contraction of the Bianchi identity. This is the Bianchi identity here, and that's all in a separate video, so I won't go into it here. Now, let's contract both sides of the field equations, of the field equation, I should say. And let's start with the field equation. Let's add in our term here, cosmological constant, and let's multiply through by metric with both indices raised. This object here, same on the other side. Just expand that out. Here we go. Let's look at this part here and see what happens there. And over here, and same over here. Now, if we have a look here, the alpha and the alpha go, and we're left with R, one index up and one index down. So rank 2, the mixed tensor of mixed rank, one up, one down, minus a half times. Now here, the Kronecker delta will apply, And we'll have delta mu nu times r plus, here's our cosmological constant, and the Kronecker delta again. And over here we contracted over alpha. We've raised one index, so we have t 1 up, 1 down, so mixed tensor. Alright, next slide over here. On the previous case we had the Kronecker delta, we had a nu down here, but where nu differs from mu, this will be 0, so it's only non-zero when mu and mu are equal here. So same thing across here, mu, here we go. When we evaluate that, we get, if you look at this contraction here, gives us the Ricci scalar, minus a half times sum over the 4 coordinates of space-time, gives us 4 here, that's 1, 1, 1, 1 plus, added together, 4r plus 4 lambda, this object here, r minus 2r plus 4 lambda, this object here, multiply through by minus 1, and we will have here, let me correct that, r minus 2r is minus r, plus 4 lambda is this object here. Now we're going to multiply through by minus 1, apologies, here we go, right there. Next step, alright, in a region devoid of matter and energy we have t equals 0, so we're left with r minus 4 lambda is 0, so r equals 4 lambda. Now this tells us that we have constant curvature throughout the region concerned and is of interest in the search for the nature of dark energy. Now r has units of 1 on length squared. So dark energy is also thought to have a constant energy density throughout space and to make up 68.3% of the energy content of the universe. And whatever the nature of dark energy is, the field equations allow for a term to describe it. And that's it.